Zakrzewski from Jagiellonian University, and the title you can read.
Yes, okay, so this will be really special. If it's recorded, it will be fun. Kazi catched me the other day to force me to say something, and this will be difficult, but I was told to start very slowly because there will be a guest to introduce to the subject. So I will speak a little bit about how much time do I have? This is the most important question. No, okay, I worry about you, not about me. Okay, so I will speak about Bose-Hubbard model and about some of the methods which are used when one wants to, let's say, more precisely describe the physics in optical lattices in tight binding approximation. Okay, so standard approaches with Bose-Hubbard. So just as an introduction to people who don't know what Bose-Hubbard is. So when the most important thing is that I did nothing, the things were done by these guys. So Mateusz Łącki is finishing a PhD, Jan Major is starting a PhD, and these two guys finished a PhD long time ago. And in particular, Dominik didn't finish PhD with me. But we are still collaborating. So what I would like to talk about is, well, make some kind of introduction to the Bose-Hubbard. To say something which we did recently about the standard Bose-Hubbard, which may be a little bit surprising, and it's simple. So just to have something simple. And then there's some motivation why to go beyond Bose-Hubbard, and I would like to present on glance two approaches which are possible. One is variational time-dependent approach, which is not ours, and which doesn't work, and effective multi-orbital approach, which we did something, and which also is not working. So then there will be some conclusions. So what is the optical lattice? I am ashamed to show this picture here, but still this is the introduction. We have the atom which interacts with light. So the dipole moment is induced in the atom. So the atom in fact is in the potential, which is proportional to the intensity of light, and inversely proportional to the detuning, which is hidden in this susceptibility or whatever this parameter, polarizability, which is here. So when if you have this intensity of the light coming from the standing wave, then you may have such a pattern, and either at the maxima of this intensity or at the minima of this intensity, depending on the side of delta, we can, but always at the minima of the potential, we can somehow trap the atoms together. And of course, normally one has the atoms also in some kind of harmonic trap, in which they sit so they don't disappear or fall under the gravity force, and then on top of it you put such an optical lattice. And then if this lattice is sufficiently high, then the idea is just to describe it by some kind of tight binding lattice model. If I remember the order of slides, yes, so this is the famous Bose-Hubbard model, incidentally discovered not by Bose nor by Hubbard, but this was done by Mr. Gersh and Mr. Norman in January issue of Physical Review. So earlier even when Hubbard created his model for fermions. So this is one of the examples of famous theorem saying that the names of models or discoveries don't go after the people who created them.
This is called the Matthew. Yes.
Yes, precisely. So this is a quite good example. This paper has been cited 5 times. I hope to cite it the 6th time.
Are you sure it wasn't discovered before 63?
No, I'm not sure.
Yeah, I mean, I'm probably.
I just was told about this paper, so I advertised, because of course I didn't find it. I mean, it was found by some German guy who worked heavily over reading all physical review letters, physical reviews. Okay, so the model is simple. You have something which describes the hopping between sites in the lattice. This lattice is here somehow represented in Immanuel's blog picture, stolen from some of his slides or over the internet as such egg cartoon. Okay, and then we have hopping between different sites. So atoms disappear, let's say, at psi I, and appear at the nearby site, which is I+1 written for one-dimensional model, but here we have two-dimensional models. So it should be some J which is near to I. And then there is the reciprocal Lagrange-Ashur's Hermitian conjugation.
And this so far is a tight binding model.
This is tight binding model.
Yes. And it is relevant what are eyes. I mean, whether they are boson or fermions.
Whether bosons or fermions, it's just a commutation relations
Yeah.
for A and A dagger. I am sorry, I introduced the subject of Professor Turski with this model, so we will discuss. Yes, okay. And then there is the second term which considers the interactions of atoms among themselves. So of course they cannot interact with themselves, so they interact with each other, so they must at least two of them. So this is the term which comes out here, and there's a strength of interaction. So the Hamiltonian is somehow very simple. And what is interesting is that it is not soluble, that's one thing. And second is that it shows the so-called quantum phase transition. So there are two ground states which, depending on the parameters, differ in their properties significantly. So if there is tunneling dominates, so interaction is small, this U is small, so then the atoms, the kinetic energy term, which is roughly this tunneling, dominates in the Hamiltonian, and this is the superfluid state, where the number of particles at each side may vary significantly. Even in this limit, let's say, of vanishing U, this is a coherent state in each side. And then, when you change this ratio, then at some point, the strong repulsion between atoms, when this U is positive, strong repulsion between these atoms forces them to be as far as possible from not occupying the same side.
Isn't that not too much to call it superfluid? Because if U is equal to 0, this is just a free particle
This
model.
is free particle
So
model,
why do you call
which
it?
is because it is totally coherent. The coherent length is infinite.
So nowadays it's fashionable to call a free particle superfluid.
Yes, yes, to some extent.
Is this obligatory in
No.
Krakow or it's
it's even not obligatory in Warsaw.
No, in Warsaw nothing is obligatory.
No, in Krakow it's also not obligatory.
I wanted to check next time I go to my hometown.
No, there is no problem if you don't call it superfluid. In fact, you can define something some property which is superfluid fraction. I don't want to go into these details because then it's I'm getting out of the subject totally. Which properly defines the superfluid properties, and then you simply move this, you make the Parrish substitution, you check the superfluid fraction, and the superfluid fraction is very large. So there are some measures which
the reason why I ask
But
is
for here it's sufficient to notice that atoms are delocalized.
yes, atoms are delocalized. But I think this superfluidity is not the subject of my talk, so this is why I want to skip.
No, I was just amused by the name.
No, but also all atoms occupy the same
So what?
orbital. The same
But
orbital in the ground state.
but
Okay, so this is also-
that's not superfluid.
Yes.
But this is not superfluid because they calculate this.
No.
And if you put up a
Okay, so similarly, one can, but there is another limit in which these atoms strongly repel each other, okay? And then this is the insulating state, because there is a gap, proper gap. And it's easy to see that if you have, let's say, mean occupation equal to 1 in the side, just for simplicity, and this is the case which I will be mostly considering later. So if mean occupation is equal to 1, then you see that this term contributes 0 to the energy if just one particle sits in every side. So it is somehow minimized if U is positive. While if moving one particle from this side and placing it here adds the energy U in the limit of J, vanishing J. So this U is really the measure of the gap for very small J's. And this is the Bose-Hubbard model, which was studied in several thousands of papers. This transition from here to there is so-called Berezinski-Kostelis-Towles type of transition with known strange properties. What we wanted to look at is a measure which, let's say, is related somehow to Laflamme, who was giving a lecture in the morning, because it's somehow related to quantum computing. These people introduced something which is called fidelity, Fortunately, I don't have to translate it into Polish because in Polish sometimes it's translated as a wierność, which is a funny name. And then what is proposed to characterize or find the position of quantum phase transition is to calculate such a fidelity, which is the overlap between the ground state at some value shifted by small parameter delta to the left and to the right. And then the idea is the following, that if we are far from the phase transition, then if this delta is small, then overlap between two ground states is large, it's practically close to 1. Okay? If you are at the phase transition, then the topology of the ground state changes, so you have rapid changes of the wave function, and this fidelity should go below 1. So when, instead of calculating some correlation functions, stuff like this, maybe it's enough to find the ground state and calculate such fidelity and localize the position of quantum phase transition. So it was proposed by these guys, let's say around here, or maybe somebody else earlier, I don't know, and tested on several models, on Ising, there should be comma, XY, Heisenberg, Kitaev model, whatever you want, a lot of models, and in fact, it really points out to the quantum phase transition, provided some finite scaling analysis is done. If you have nice scaling law about, say, power correlations of close to the phase transition, then you can get also a nice scaling law for this F.
What is lambda?
Lambda is the value of lambda is the value of the parameter. I have a Hamiltonian. And I have some, depending on some parameter. In my Bose-Hubbard model, I will have Hamiltonian depending on, say, J. Or J over U, because it is the only parameter, the real parameter. I'm sorry, very good question. My only parameter is J over U in Bose-Hubbard model. And when I change J over U, find the ground states, and compare the ground states for close values of this.
There is another parameter in your model.
Yes, sir. Number of particles.
Number of particles, n.
Yes, number of particles and number of sites. Number of sites is n, number of particles is n.
Yeah.
Or vice versa.
Therefore, it's not true that there is only one parameter.
In the thermodynamical limit, when n and n go to infinity,
okay, you didn't say thermodynamical.
I apologize, I didn't say in the thermodynamical. Everybody has heard that I didn't say in the. This will be something, okay? I will come to this is we are coming to this, okay? There is a problem for Bose-Hubbard model because this is not a kind of phase transition which has power law correlations. If there is a gap on one side,
and since this word Ising model is mentioned there, then there's another parameter. Which
I'm
not speaking about Ising model. I speak
always
say Ising model, not Ising, because we are not
there is also dimensionality.
Okay. In this power correlations,
so are we talking about the Hubbard model in one dimension or two dimensions?
We are talking now as the Bose-Hubbard model in one dimension. On the numerical example which I will show, and starting from here, we are talking about Bose-Hubbard in one dimension. Still, the correlations are, for example, this PKT transition for Bose-Hubbard is only in one dimension. This is the problem which we are studying, looking at now. Okay? So the question is, since this Bose-Hubbard in one dimension is difficult because this is somehow it doesn't, the phase transition is strange, let's say, then the question is whether this fidelity will work. Okay, for the Bose-Hubbard. There were some numerical evidences coming from these two papers, which people has shown some results for this fidelity for small systems, and then claimed that if they fit something in the limit of n over n going to infinity.
Correctly, this definition is that I take a Hubbard model in one dimension, I find approximately ground state for a value of j over n equal to something, and then I take another value which is slightly different, and for some reason I calculate this.
I calculate this overlap.
This overlap, and that I call a fidelity.
Yes, if you agree with this definition of Mr. Zanardi, and his...
No, I mean it's a definition. So
yes,
I don't agree or disagree with
yes, but we have said it already.
No,
we have said it already 10 minutes ago. So yes, we do it this way.
No, I'm trying to.
Okay.
Hubbard model. So
Okay.
this lambda and delta together is j over n and j over n plus epsilon.
Yes.
J over U.
Over you.
J over u. I'm sorry, j over u.
If I may erase this, then what is there? Lambda is j over u, and delta is some delta j over u, which is small, which we add here or subtract. Okay. So then what we can do is, if this delta is small, we can make, assuming that this is analytic, we can make the expansion around delta, and there will be the first term which appeared here, for obvious reason, will be delta squared. And then this thing which is this chi, which is here, if this is fidelity,
And
this is, let me finish the
This
sentence.
is a general definition, or
Let me-
this is
Let
a
me
fact for
finish
the
the sentence, please. This chi, which is defined by this, let's say, relation, is called fidelity susceptibility. Please.
Yeah, but I mean the fact that this
this
f of lambda delta is equal to this is
this is the definition of f.
for any
any
quantum mechanical system.
For
this
any
would-
quantum mechanical system, you don't have to have phase transition, you don't have to have anything. In quantum information theory, they define something which is called fidelity, and this is its definition.
yeah,
So this is the quantity which measures the linear response to the changes of the parameters of the Hamiltonian. So we can apply the linear response
I
theory.
mean, in a general system to some parameters, because most of the
Yeah,
models.
so we take one parameter, J over U.
But let's talk about the
Yeah.
Hubbard model.
So we take
In
this.
a Hubbard model, this says that it is there is a universal function of j of u, and if I change the j of u a little bit, then I will have this.
I
result.
would not like to say that this is a universal function. I am saying that this is, I define
No,
such a
this is
function.
a universal function. There is a certain I have a Hubbard model with j over u,
Yes,
which is called lambda.
yes.
Okay.
And then I have,
f defined this way cannot be bigger than 1, obviously, right?
Yes.
So its expansion for tiny delta must start with a quadratic term. That's trivial.
yes.
It's not physics. It's elementary mathematics.
Yeah, but the fact that lambda.
It's symmetric in terms.
It's also symmetric in the delta
Yeah,
minus
of
delta.
course.
So
Delta
this
equals
is-
0 is extreme.
I mean, I don't see the point of discussing. I mean, this is the definition of an object, which is. And
First
then,
derivative is 0, obviously. Because
yes, and then you just expand the first term if something is behaves like cosine or something, but it has the square as a first. So this guy is called fidelity susceptibility. And one thing which one can do is try to find it analytically. The problem with Bose-Hubbard is that almost nowhere you can find anything analytic. So but we have Bojo-Damski. So one limit is somehow trivial. For J going to 0, we have so-called, which condensed matter people say atomic limit, which means that the sides are decoupled and you can calculate everything on one side. And then one can find that this guy which is here is given analytically by such formula, which n is the number of atoms and bosons, n is the number of sides. So you see that it is extensive in m. Let's say it's just, if this is 1, n over n is 1, but this is extensive with m is other.
I have a question. This result is valid only in one dimension or?
On one dimension. In one.
Everything is
Because
in one
it
number.
No.
It is.
This is one dimension.
One-
One dimension. All this is one dimension. All this part on fidelity is on one dimension. There is other non-trivial limit, which is when u over j goes to 0, which is difficult to calculate. But there is Bojo-Damski rewrote one of the chapters of Grashstein-Rizhik, so now he has a table of his own sums, which he calculates at night. So one of the sums of his comes to this form, and yeah. maybe he will find it, okay, but it's not this one. And this is hyper-extensive, right? So this is kind of, it's proportional to m squared, so this is, or to m fourth, so it is non-trivial result, let's say. And then well, one can try to do some Bogoliubov to standard approximation over the mean level state, but it doesn't work well because in mod phase you have a gap. You can try to...
Can one understand why this is this quantity has this funny behavior?
Why this sky is such a behavior? No, but it will be more funny even later. So please let me... well, what I wanted to say is that whatever approach you try, you cannot calculate the sky reasonably. There were some guys who tried to use Luttinger liquid, sorry for this spelling, Luttinger liquid approach, but then some people claim that in the thermodynamic limit they have some results. There are other published papers which show that apparently the thermodynamic limit depends on parameters which you how you approach this limit, and that simply there is no good results, and even the guy explained why this is no good results. So we just wanted to do the numerics for it. And there were some papers with the numerics, but they were for much smaller system. So when you have some numerics which is done with something which for specialists is called the density matrix normalization group, or TBD with imaginary time, we can do it with, in fact it was TBD, with open boundary conditions, which I will call OBC, or periodic boundary conditions. So this is how this fidelity looks like as the size of the system or number of particles, because it's equivalent, increases. So you see that, well, the number of particles is smaller than something like this, and then this develops a shallow minimum somehow, which you can trace, and let's say find the value of this minimum and the position of this minimum, and hoping to find the phase transition. So these are the open periodic boundary conditions. You also see from the numbers here that we are reaching this fidelity of the order of 0.4. So this expansion 1 minus chi delta square over 2 is of course not valid in this region. But we are looking for total fidelity, so it doesn't really matter. The funny thing is, which is unexplained, and you are welcome to find the explanation, is that if you look at the value of this fidelity at the minimum, if you choose the minimum and look at this value, it is fitted with very good accuracy with such a nice formula. We don't know whether it is m or n here, number of particle or number of size, since we are in situation m equal to n. So we wrote here m, we could write the n. There is this delta parameter which is the size of our step in J, and some numerical constant which is here. The fit is magnificent. We don't know totally why it is so.
This is the feature of Stabilis transition, I think. Because normally in the second order phase transition you have the critical exponents and so on. And
here you don't have.
Yes, you don't have, because this
but well, this is good guess, but this is not a proof. I mean, such a statement. I don't know if for every case.
Because this is the infinite order phase transition, yes?
Yes, but why it should scale this value of fidelity scale exponentially like this with the square of delta, I don't know.
What is J star?
J star is the position of the minimum. Where is this minimum here? This is.
So it's J over U.
J star over U.
Okay.
U is kept fixed, we change J, so we call it. Okay, very good. We could call it J over U star. It will be more precise. Fortunately, we were not our referring. Because we will be one more change to do. Okay. Then for periodic boundary conditions, we cannot go to such big systems, which is technical problem, because if you close the system on the torus, then all these algorithms are, let's say, 60, 100 times slower, which I'm talking. Well, there are papers several papers, 10 papers or 12 papers, how to speed up density matrix normalization group for periodic boundary conditions, all are wrong. So you can try these things and they don't work. So we could reach after, well, let's say a month of calculations, for periodic boundary conditions something like m equals 64, and you see that this, so when we are in this high fidelity, let's say, limit in this small deviations, but you see that the minimum is much sharper here in this case as compared to open boundary conditions. But then, well, we want to check whether you can find the phase transition, and by going to the in the limit, and then the phase transition, the critical value.
It's a one-dimensional model.
Yes.
With a short-range interaction.
Yes.
So how it is possible that it has a phase transition?
It has.
No.
It is.
No, I mean, this numerical behavior is not the proof.
But it is not. It is not my. I am not proving that there is a phase transition. Kosterlitz-Towles phase transition for Bose-Hubbard, because there are 10 or 15 papers which have proven this, and so I don't. I leave this aside. This discussion whether this is phase transition or not, whether this is Bose-Hubbard or something else, because I cannot fight with the literature. I cannot show you correlation functions. Everything agrees with the theory agrees with predictions. Everything is fine. About the Bose-Hubbard model.
But there are simple tricks or rules to find out whether the behavior of a susceptibility is related to the phase transition or not.
But so it is checked that this is.
Yes. For example, it is checked that this is not the Schottky anomaly or something like this.
So it is shown, for example, that this one-dimensional Bose-Hubbard model on the tip of the transition is in the same universality as two-dimensional XY model.
Yes.
And therefore, this is the Kosterlitz-Towles transition.
Yes.
This is the answer.
On the tip, which means that if you plot the, well, I have it somehow 50 slides later, but we will not reach this stage, so there is not a problem. If you plot this J over U, and here you have chemical potential, if you would like to have the plot, then the plot looks like this. This is mod insulator, the rest is superfluid. This is mod insulator for n, average n equal to 2. This is average n equal to 1. Well, they should touch here somehow, like this. This is what is called superfluid by the broad community, and this is the tip, which is somehow around 0.3.
But the reason I'm asking is
and there is going along precisely along the line with
this would be another example of the fact that the quantum phase transition is d-1 dimension.
Yes,
and
exactly.
that's what I'm trying to yeah, I mean that's what I'm trying to understand, and maybe this is not so obvious to the rest of the audience, that there is some kind of a rule or assumption that if I have a classical phase transition in d dimension, that there is a one dimension less quantum mechanical.
Yes, precisely.
So that's what I wanted. This is what I wanted to pick it up.
Okay. So then if we have this point which is the minimum, so we would like to make the thermodynamic limit. Okay. So go to the largest size possible. So then these are the data points for for different sizes of the system, and you can fit them by the red curve, which has no logarithmic correction, and by the blue curve, which is slightly better. And this is kind of expression which we fit with some logarithmic correction, with errors like this, and the value of this phase transition is 0.21. Not the value of phase transition, the value of the extrapolated to infinity thermodynamic limit, the position of the minimum of fidelity. The phase transition position is around 0.3. This is 0.297 according to Dominic and me, let's say 5 years ago, and somebody else calculated now a little bit better, and they claim it is 0.292 or something, but it's certainly far, far away from this value. That's obvious. If you look at fidelity susceptibility for small deltas and increase m, and you plot this, then others, because they also observe some discrepancy, but they observe that these guys cross here somewhere at the magic point which coincides with the real value more or less of phase transition. Except that for us this is just the total coincidence. Okay? Because there is no grounds on which one can say that this cross is okay, and all these results are for open boundary conditions. For periodic boundary conditions, despite the fact that what happened with my periodic boundary conditions? It disappeared. Yes, there was a slide about periodic boundary conditions, so I will explain to you. I don't know what happened to this slide. Maybe it disappeared in the train, which was going from Krakow to Warsaw. First of all, there is no such crossing. There is no such crossings in periodic boundary conditions. So there is this is just artifact for open boundary condition. We have much smaller sizes, up to 64. So of course we cannot make the feed with this accuracy, but the obtained value, you have to believe me in the numerics. I have the paper somewhere to prove it after the talk. But the value obtained is 0.27 or 28 of this order. Within the error bounds, it agrees with the phase transition. So it seems that there is, despite the fact that the system is large, there is huge difference between open boundary conditions and periodic boundary conditions as far as fidelity is concerned. And this is kind of surprising message, because normally we say that, okay, what happens at the edges of the system if you put thousands atoms or thousands sites? It doesn't matter. Of course the wave function goes back to 0. But it doesn't matter normally, because we have everywhere density equal 1. This bloody wave function feels the boundary conditions, despite the fact that the system is 1,000 size or so large, and falsifies the fidelity, just because of the boundary conditions. And the explanation somehow can be seen in this plot, which is the, let's say, not for 1,000 but to 56 sites. It is the density of particles on the sides. For unit field, we have 256 particles, 256 sites, but we have open boundary conditions, so we have, of course, 0 here and 0 here. So then this density slightly changes here. And these modifications of density affect the whole wave function, propagate through this wave function, showing very, if you want, in the language of quantum computing, very distant entanglement of the system, and showing that all this system is totally entangled of a very large distance. Okay? So this is funny finding which I wanted to share with you. Tomek, please.
You try to do it with this twisted boundary condition, because there is this paper by Zakrzewskiego or someone from Barcelona who show that if you make this different boundary conditions with different twisting, then you can calculate the superfluid fraction in the...
No, this is not the paper of Zakrzewskiego, but there is a Roth and Barnett paper from 2002 which defines the superfluid fraction by twisted boundary conditions, and Mr. Damski calculated it using the twisted boundary conditions for mean-field model for this order in 2002 in the paper, which has 200 citations. So we started with this order. So there is okay, if you calculate the twisted boundary conditions, then you will get the superfluid fraction. You may probably get the position of the, with some precision, the position of the phase transition point. I never attempted to do to compare the accuracy which you get with the accuracy obtained from correlation functions. Because what we know from the theory, from Kostelis-Taules, and from Luttinger liquid theory, is that the correlation functions decay as a 1/4 at the phase transition. It is exact result. So when it is, for me, it was easier to calculate the correlation function than to go from real to complex tunnelings with twisted boundary conditions. This is the detail. But nobody calculated probably fidelity in this way, as looking at the...
This was my question.
Yes, that's probably one can maybe look at. Okay, so how much time do I get?
Still an hour.
Still a lot. Okay. So when this was one nice subject coming about this model, but then I would like to improve this model, so I have to somehow come back to derivation of this model. So then what we do, we write the standard. Now there will be a bunch of formulas, I am sorry. I will skip some of them. We write the Hamiltonian in second quantization of the system. There is the lattice potential, there is some external trap, if one wants, and there is an interaction potential which for purists could be approximated this way, but very often is approximated by a contact interaction term. Kazik knows and plenty of other people knows that this should be better as long as we make the basis which is contained of smooth functions and we don't go to very large kinetic energy, then these potentials are totally equivalent. But purists complain if you don't write this form and throw away your paper for correction. So then it's better.
It wasn't me.
I know it wasn't you. It was Mr. Wykład. Because he asked us to add 7 papers on Mr. Wykład to the reference list. So it was obvious that it was. Okay, but this is a standard situation. We have a lattice potential, so this V here is the lattice potential, which may have different amplitudes in different directions, let's say X and Y. And in particular, the model which I was talking about was the situation like this, that you have, in fact, very strong lasers in 2 directions, producing such tubes, and then a relatively small lattice along here. So then you can realize in the experiment arrangement of tubes which are not interacting among themselves, because tunneling from here to here is practically forbidden. But without the lattice, they can just move along the line in some shallow trap. If you put the lattice, then you have one-dimensional system. You can make these 3 lattices of the same magnitude, and then you realize fancy crystal originated in Munich or somewhere else. And what then you can do in the standard way, expand the field operator in linear functions, where the alpha index numbers the bands, block bands, different block bands, and the creation operators which were therefore corresponding to site I and the block band alpha. The standard Hubbard model considers low energy states, low temperature, 0 temperature. So then there is only the lowest band. But if you make the expansion, we expand in all linear functions because we have to. Then we calculate trivial integrals, and we get the Hamiltonian, which is written here, which contains the tunnelings, which due to properties of the linear functions, the tunneling doesn't change the band. This is just because the linear functions are constructed.
No, that's the reason why they have been invented.
That's precisely.
It's not this way.
Yes, okay. And then there is the interaction term in full glory here with all the indices. If you want to have more indices, please add. It's no problem. And the energies at each side. Then these integrals are given by 4 linear functions taking at the same point because we have contact interactions. So there was this delta, which already is taken care of. And the tunnelings are in this form. The problem is that this Hamiltonian is of course nice, but it is insoluble. Okay? Because we have, it's so, even Bose-Hubbard is not soluble, well, it can be diagonalized for 10 particles and on 10 sides, and Zakrzewskiego can do it for 12 particles and 12 sides, so this is why he is so well known in this diagonalization business. But this guy is even untreatable for more than, I don't know, 5 sides and 5-6 particles. This is difficult, precisely because of these many couplings which are here, many tunnelings, whatever. So then, if you want somehow to include the interactions properly, whatever, you have to do some approximations. The most brutal approximation is in Bose-Hubbard model, when you just, first of all, you leave just the alpha equal to 1 or to 0, depending on your notation, and then you include nearest neighbor tunnelings only, which is okay. And you drop all the interactions except interactions on the side. And only density-density interactions, which was what was left. the problem is that this is, as I said, numerically intractable if I want to do it exactly. The other problem, which is with this approach, with Bose-Hubbard model, is the fact that the linear basis is really, as it was defined, non-interacting basis. So in the moment when this at the moment when this interaction starts to play the role, when this G is large, then at this moment this basis somehow is not adapted to the problem. So one has to find the ways of including interaction in the basis to construct a better model, somehow soluble. And this is the way people do things. One of the propositions was somehow variational time-dependent Bose-Hubbard approach, which consists in the following way, that you construct, for each side, you construct a linear function, one linear function, which is a combination of several band functions with time-dependent coefficients. And now you construct the evolution for this time-dependent coefficients d, and for all the parameters of the Hamiltonian, for these linear functions, from variational principle. So it is kind of nice because variational principle within given subspace is sometimes somehow optimal. Normally gives some optimal results. So these guys were very happy that they have a variational time-dependent approach. And this is kind of heavy. I'm hesitating whether I should show these formulas. So maybe I'll just show that this time-dependent variational Hamiltonian which you obtain is in fact the same Bose-Hubbard Hamiltonian, which the L here should be substituted by M. I'm sorry. The number of sides smoothly changed from M to L by copy-pasting. And so then this is the same Hamiltonian, but now we have time-dependent creation-annihilation operators and time-dependent tunnelings and interactions which are defined in some strange way. You can build the other equations, very complicated, but what is the real approximation which is here, and I would like to show you and warn you about it.
But how do you get, I mean, in order to calculate the J of t, right, you have to know how to evolve
the W's. So then what you do, okay, I know that you are interested. What you do, you expand the wave function in terms of, time-dependent coefficients and the vectors, and all these vectors are, let's say, in positional representation. In this notation, it means that there is some given n particles on these sides in different possible permutations of linear functions. And then for this guy, you write the variational principle, so you take the Hamiltonian, okay, minus it, expand it in phi's, and then you take Lagrange coefficients which are just keeping the norm of these time-dependent linear functions, which are okay. And then you can get exact equations for this evolution of linear functions and what else is different objects which appear here.
But the finally object of the study is the property of the ground state, yes?
Yes, obviously if you start from the ground state, yes. Yes, I will show examples on the ground state.
So
but
what
the ground
sort of time dependence are you talking about? Physically?
Yeah.
Physically, depending what I want to do. If I want to, I can do it in imaginary time to get the real ground state. I can change the parameters in the system, and then my linear functions adapt. For example, I can change the height of the lattice, and my linear functions will adapt.
You can see how this changes as you change the parameters of the model.
Yes. For example, I can start from the model which is from the ground state at very small interactions, where interactions don't play the role, and then increase the interactions and see what are the properties of the ground state.
To nie jest czas, to jest...
This
may be diabatyczna zmiana parametrów Hamiltona.
It may be thought sometimes as change of some parameters, not necessarily adiabatic. It doesn't have to be adiabatic.
Okay. Well, come on, it's this kind of variation principle, so what else it is?
Now, let me, I was suspicious about this guy. At the moment when I saw it. Why? Because somehow instead of this is very rich structure here, and somehow you all particles at a given site are represented by the same time-dependent linear function. Okay, so it looks like some kind of mean field. Okay, because they are all in the same state. I don't like it because I can imagine that I have 5 particles at the site, where let's say 2 are in the ground, in the lowest band, and 1 is in the first excited band, and so on. And this changes in time, and I cannot explain it by a single linear function, because otherwise they all behave the same way. So there are certain limitations of this approach, which I wanted to see, but nobody tested this approach because it's complicated. Okay. So if you write very complicated paper and you get through, then you are relatively safe.
And you publish it in a crazy paper.
Why? No, this was published in very good, relatively good journal, which is New Journal of Physics, and which, well, okay, at least by the Ministry of Higher Education in Poland, it is better than Physical Review, except Physical Review C, which is nuclear physics, which is on the level of Physical Review letters. If you ask me why, I can tell you in private, probably. But you are intelligent enough to find it by yourself why it is so. So I will not say anything and come back to physics. So we employ this ansatz, okay, for very simple system for which we can control approximation, okay. So our system is 4 sites and 6 particles with many bands. Okay? And then I find the ground state as a function of interaction strength with G, which is for rubidium typically of the order of 1, 0.87 or something, of the order of 1. But well, nobody, well, I can use flashback resonance, I can use anything you want, different system, I can have bigger G. And then this is the dotted line is the ground state of a Bose-Hubbard, standard Bose-Hubbard model, which is as the reference for us, okay? So this is the flat, because it changes rapidly with G, but I don't want to have this rapid change on the axis, so this is my reference. 1 band in many band expansion, okay? Then I have this variational principle ground state, which is obtained here. This red dashed line comes from this variational approach, which after, if you take 3 or 4 or 5 bands here in this expansion, it doesn't matter, you get the same result. Already better is standard 2-band expansion, well, this standard multi-band expansion reduced to 2 bands. If you have first band and ground band and the first excited block band, it gives better accuracy, and of course it starts to converge to the ground state when you increase the number of bands. If you this 5 bands is already something like 40,000 by 40,000 matrix, so it is enough to make the patient student impatient. So you cannot go much harder, and there is no point. Apparently the method is not working too well for large G. Well, it's comparable to first 2 bands for, let's say, moderate Gs. What one can do is study the time dependence when this parameter T is really the time dependence. So you prepare some state, which is not the ground state, some initial state. For example, 2, 2, 1, 1. You have 4 sites, 6 particles, so this is quite nice state, Fock type, with periodic boundary conditions. And then if G is small, you evolve it along the black line, which is the variational calculation, or along the red line, which is the red or green, depending on the position of these particles for multi-band expansion. Okay? And then for small G, you see no difference. The variational method and the multi-band work together. For larger G, well, there is practically no correlation between the, well, this is occupation of one side goes from 1 to 1.5 half, in a regular way in multi-band expansion, and the other side goes like this, while the behavior is totally different with this variational ansatz. It doesn't catch the physics for the strong cutting. Another example is something like this, when we quench the G from small value, this G, from small value to, let's say, 10 for different times. Okay? So when we look at the final energy as a function of the quench time. If we quench very, very slowly, we should follow the ground state. Okay? And then if you quench very slowly with, now the colors are changed, if we quench very slowly with multiband expansion, we land somewhere here, and variational approach gives the ground state of much higher energy. Okay, so this just shows that this variational approach is not too good. So then, what one can do, one can improve it. Let's try to improve it. We took one linear function per site. So the simplest way we can try to improve it is take two linear functions per site, rewrite the variational condition for the larger Hilbert space which you take into account, and maybe this will improve things, because at this we will have some positive result. I am sorry to say that it improves something, because this is the result for one band this is this new Journal of Physics Centrum, let's say, group result. If you work on this approach, you include two bands, you get somewhere here, but this is still, which is far superior to this, but is inferior to 3 or 4 bands multiband expansion. So this variational approach is simply not working, and is, in our opinion, simply not worth investing in. And why? Because this really, if you have strong interactions, when the particles get strongly correlated, there is some kind of multi-particle entanglement, and you need many functions, combination of many functions to describe this state. You cannot make some kind of an answer like this. So it is kind of depressing result. But
what was the lattice depth here in the simulations? In recoil? It is shallow lattice or deep lattice?
No. It is rather of the order of 20, I would say. I have a number which.
But it is deep lattice.
No, it's relatively deep lattice. Yes. So somehow this interaction is with higher bands is important. Okay, so last approach which I would like to just tell you a little bit about is other approach which many people contributed, which I listed on some of the papers, how to modify the linear functions to take care of the interactions. And this is again other approach of Centrum. This is very nice early paper of Phillips group, experimental, which showed that the interaction between atoms depend on the number of atoms which are in a given site. So this interaction constant, which you can measure somehow, was different experimentally. And this was, I guess, the first paper which showed the importance of the interaction for one. In fact, there were several modifications with several friends listed here. And we somehow made some small contribution to this. So again, we look at this awful Hamiltonian which is here. Sorry, I didn't repeat it. This one. And suppose we know that we cannot solve exactly the interaction problem with multiband system. So what one can do, and this is in consistent way was done by Bisbord and by Dilbruch and others, is to, let's forget about the tunneling first. Let's consider the deep lattices, forget about tunnelings, and when we are on single site, we can diagonalize the interactions and build the proper wave functions. If we can build this proper interacting wave function on a single site, then later we will allow for tunneling, and maybe we will have some model working. I don't know if I will have time, so I tell now, but of course this procedure may work only for moderate interactions, because once you mix several bands to very high level, then the tunnelings are not only to nearest neighbors, but of course the particle in higher bands can go very fast, and all the tight binding expansion practically breaks down. So we are not going into the limit of G being theoretically large, but we have to look at moderate Gs. And then we reduce ourselves to interaction in a given site, and look at this interaction. What are the possibilities of the interactions? We will also have, first, okay, so I will come to this point later because, so we treat this local system, we diagonalize it, and obtain indifferent particle number subspaces, because particle number of course is conserved, we get different ground states. So we have a ground state for one particle, for two particles, for three, for four, and so on. And we can compare this ground state and somehow try to express it in a nice way. So one way of expressing it is that the ground state, let's say, is we have n particles with some energy E0, which is the single particle energy, plus some term which is proportional to n minus 1, just to recall the Bose-Hubbard limit. But depending on n, this constant u is not a constant, but really is depending on n. So it is cheating the model, but this way we can define u for different n's. This is equivalent, such an approach is totally equivalent to the fact that we write this energy and express it in a single energy term plus u2 and have n minus 1 plus some different coefficient which should be called with different letter and call it n minus 1 and minus 2. And we can call it the effective free body interaction. And then we have effective four body interactions, and we can have such a series coming from this diagonalization. And hopefully these coefficients will behave reasonably, and we can get these coefficients from diagonalization. Later we will include the tunnelings. So what are the tunnelings? First we have the I'm sorry, I have the order of the slides not too good. First we have the normal tunnelings, which were G, and then there is other terms which were forgotten in the Bose-Hubbard approach, but which are very well known in condensed matter because they were done by Hirsch, the same Hirsch who invented the index. So he did the bad thing, but he also did good physics. And good physics was that there are terms which connect the sides coming from these interactions. And in particular, there are terms when you take one annihilation, one creation operator from one side or the other, some kind of a tunneling, and then the occupation on the side, because you have a choice between A and A dagger. So you always have to take two A daggers and two A's, but you can take one A dagger from one side and one A from the other side, and you still have the tunneling plus the density. And these terms contribute in such integral forms to the tunneling. So
yeah, but then,
I can write it down.
There is a physical argument for this Hirsch term, if I remember, for particular kind of Fermis. I mean,
he did it for he did these arguments for electrons.
Yeah, and there is a reason for it, because then we know exactly what the U is. It's a Coulomb energy.
Okay.
And this model has a very. It's not universal in some sense. It refers to a system which has particular band structure, which has particular behavior of a dielectric function. So, I mean, why should you all over the sudden bother here? Because I don't remember exactly everything.
Okay. I will show you why.
I'm not going to give an impression that I know the paper by Hirsch now, details. But as far as I know, it clearly is in 3 dimensions.
Yes,
It's not in 1 dimension. I believe it does not exist.
Okay, now I smoothly changed to 3 dimensions, but it doesn't matter really. Hirsch is just the type of a term which is given. But
yeah, but this term,
I will show you. I will show you experimental results which show that this term is very important. Also,
even in 1 dimension,
not in 3 dimensions. In 3 dimensions, but also for contact interactions. Not for long-range Coulomb, but for contact interactions.
This is interesting because the long-range interaction producing terms that link different sides is kind of obvious.
Yeah, that's what
here it is not.
No, but here it is not.
I understand. I mean,
okay, well, you write this.
I'm right. I remember it correctly. This always. I mean, after all, we should not forget.
In other words, you are giving too much credit to Hirsch. That's what he said.
Yes. Okay. I should give credit to dear Gluckman, and other
I
guys.
don't care so much about names and credits. I mean, I'm trying to understand the physics.
Okay, so this term, which was important for Coulomb interactions in
some cases,
and was called bond charge tunneling in this language. I don't use this, I use density-dependent tunneling because I don't have charges, my atoms are neutral.
Yeah.
So I don't like to speak about charge density waves, for example, which people use in cold atoms, I don't know for what reason. Because the atoms cannot have charge density waves, they have density waves.
Because they have lazy referees who will not reject them.
Yes, but this is just discussion of nomenclature, okay, of semantics. But the term exists, and so when you use
But then
this,
physically, if I have this just contact interaction on the lattice, right?
yes, okay, I will explain.
How come this simple?
Okay, I will explain if I may. If you give me
You
the
can
chance.
think about the crowding, but not.
Okay, I have one linear function at site I. I have other functions. Let me write one of these terms, okay? At different site, and so the term is Ni, Ai plus Aj dagger, something like this. Okay? No.
Nie.
And on everything, everything comes out from the fact that these banners extend a little bit over the next side. A little bit, not much. So these terms are not large. They are a fraction, small fraction of J. But
so the overlap of the functions is not short range, right?
Overlap is not short range.
Extends over.
And
So
the
sum over Ij goes over this little bit of the tails which overlap.
Yes, and this is maybe peculiarity of sign potential. Maybe if you take other potential which has not the pure sign shape but something else, it will have
kind of
steeper potential. It will be totally neglectable.
And that, of course, is what corresponds to how Hirsch got it. He got it for a very peculiar model. So this important. Yeah, I'm sorry.
Okay, so let me just show you. So when you can build the effective Hamiltonian, and this is what I just wanted to show you some results to show you that life is not simple. For example, this is just the diagonalization on one side. Results for 3D-dimensional lattice, some peculiar parameters. Lattice depth is weak. Rather, for how many this is inverse of the band number. How many bands you include? So you include 4 bands, 5 bands, 10 bands, whatever, something a little bit more. And this is the value of coefficient UN in units of the value of Bose-Hubbard coefficient because it's natural. So for single band calculation. And when you see, if you take the standard diagonalization approach, you take the basis and you cut it at some energy. So you take the lowest states in energy, as chemists, quantum chemists do. You somehow from the base take only the states which will mean energy the smallest. Then you get these dashed lines, which apparently show you the convergent results. You increase the number of bands that you saturate. Okay? But then you can change the basis and look at which states are coupled perturbatively to which states, and make the diagonalization which is, let's say, physical coupling oriented. And with the same basis, so already something like 40,000 states, 40,000 states, then you see that you converge to slightly different results, which is, let's say, 5 or 10% different from the other diagonalization. So it is tricky to get these coefficients. One can get these coefficients, and this is the experimental result, dear Professor Tursky. People measure so-called quantum revivals. How they do it? They prepare the system, let's say, at very low lattice, when the state is almost superfluid. I mean, there's a large fluctuation between number of sites. Let's say at 3 energy recurrence or 5 or 7. And then you prepare such a ground state, and then you very sharply change the lattice to very high value. So when this wave function, which is a combination of several states, evolve in time, acquiring a phase, which you can see this evolution here, and then you can extract what are the energies of the states by like the standard quantum revival from let's say harmonic oscillator, and then energies are extracted here, and the dashed lines, which if there would be only one U contribution, then there will be single peak. And these are the peaks observed experimentally by Fourier transforming the signals, and the dashed lines are the calculations of Dirk Luhmann and well, Dirk Luhmann and Dirk Luhmann, okay, because the rest of the group was experimental, so he had to do it. And so this is how good fit is. So this is Nature paper which kills the discussion that I say about the on-site interactions. You can calculate also how they depend on the tunnelings. I don't have time. This is funny plot which we have got with Mateusz, which is the mean field phase diagram for this Bose-Hubbard. Normally, mean field phase diagrams depend only on the number of neighbors. Okay, if you make this standard approach, numbers of nearest neighbors. So there's a parameter which counts how many neighbors you have. And then you can rescale from 1 dimension to 2 dimensions to 3 dimensions exactly without any problem. Now, even doing the field calculation, we are doing it with system which has different interactions than different dimension, because if you have 1D, then you have tight binding in perpendicular directions, and then this thing is difficult. You can also look at phase diagram without mean field. So this is this phase diagram which I drawn here in standard Bose-Hubbard, and this is with the energy, and you see the difference between the two. And I stop here showing you some kind of conclusions that I cannot forget about this, because among these people in this room there may be some future referees of the final report from the grant, so watch out, better give the credit to where the money comes from. It's possible to get some effective solutions for strong interactions. This is, however, very difficult for polar molecules, which I didn't explain. And then there is plenty of things which can be done, which are not understood and are to be done in the future. Sorry for speaking too long.
Thank you.